for the main event, so to speak. So we are so happy to have one of our former colleagues here, Dr. David Daniel, to talk about reflections on lessons learned from a career in geotechnics. Dave has a lot of strong connections to UT, I'll say. He did all of his degrees here at the University of Texas, bachelor's, master's, and PhD. And then he served on the faculty here at UT for 15 years. After that, he went to the University of Illinois from 1996 to 2005, where he started out as the head of civil engineering and ultimately became the dean of engineering at the University of Illinois. After that, he spent 10 years from 2005 to 2015 as the president of UT Dallas. And I think what we see here is someone who's really been able to rise up in these important administrative roles in academia, not just on the research side. So I'm really interested to hear more about that. After UT Dallas, he spent a few years here back in Austin for the UT system, working as the deputy chancellor. So he's really had a unique and broad experience across academia. Many, many awards, another member of the National Academy of Engineering, involved in some important technical professional service, some of which I think we're going to hear today about the Deepwater Horizon. And he's currently the president of the the Academy of Medicine, Engineering, and Science of Texas, TAMIS, which is kind of like the NAE of Texas. So without further ado, I'd like to introduce Dave Daniels. I will stop sharing. There we go.
Ellen, thank you so much. Can you hear me okay?
Yep, can hear you just fine. I'm going to mute myself.
All right. Well, Roy, it's great to see you. And Bob, you're up on my screen as well. Let me see if I can share my screen, see if this works. And Ellen, you're going to tell me if anything's not working. Does it look okay?
Looks great. We're all ready to go. Thanks.
Okay. Well, let me thank you all for joining today. It really is an honor to be the Reese lecturer this year. When Ellen first contacted me a few months ago and asked me if I would do it, I paused for a minute, and I'll tell you why. I first heard the Terzaghi lecture in 1975. Meyerhoff was the lecturer. He, of course, is famous for his work on bearing capacity. And I remember vividly, actually, I was with Roy Olson. It was the ASCE meeting that year, Roy, when you won the Norman Medal. And I remember thinking it sure would have been nice to have heard Meyerhoff at the height of his career. The Terzaghi lecture was actually like 20 years after he had done his significant work. So my hesitancy, Ellen, was just I'm 20 years or more past my geotechnical engineering work. And I'd already talked about my research in the Terzaghi lecture in 2012. So I wondered what I would talk about. But I accepted, and I do want to talk about things that I'm thinking about today that are still current for me. And I decided what I'll do is reflect on some of the lessons I've learned as an engineer and as a student, actually, that turned out to be much more useful to me than I might have realized at the time. That's sort of the first part of the lecture that's really intended for students and young professionals. For the many of you who are on this with your own experiences, I'm sure you have your own lessons learned, but I'll share those with you quickly. Then I'd like to jump into the Deepwater Horizon disaster. I served on the National Academy of Engineering Committee that reviewed that disaster, and there are some, I think, really important lessons to be learned from that. And then I'll wrap it up with some final reflections. You did see most of these folks in an earlier photograph, but just sort of to trace the history, I showed up in 1968 as a freshman at UT. Dr. Wright joined the faculty shortly thereafter. By the time I got to be a junior and started taking the civil and geotechnical engineering courses, he was on the faculty, as was Roy Olson. Ken Stokey joined about the time I got my master's degree and left to go work in engineering practice for 3 years. And thankfully he was there. You'll hear about that. Priscilla Nelson was a really valued colleague on the faculty. She was so much fun to be around. She's at the Colorado School of Mines right now. Actually, her last day at UT was the same as my last day, as she went off and did other things. And of course, I had the great pleasure of knowing and working with Bob Gilbert while I was still on the faculty. He's the head of the civil engineering department now. And as it turned out, I got to know Ellen a little bit before she joined UT. So these are the folks, especially Doctors Reese, Wright, and Olson, who really got me interested in geotechnical engineering. So for me as a junior, I took the introductory geotechnical engineering class from Dr. Reese. And he caught my attention because one day he brought a beaker full of golf balls to class. And I should tell you, I've been an avid golfer ever since I was about 12 years old. So he immediately was a good guy as far as I was concerned because he was a golfer. At any rate, he showed some golf balls and explained effective stress as the weight, if you will, or pressure between the golf balls. And in the dry condition, of course, the golf balls have a certain weight against one another. But when you submerge them below the water surface, they're buoyant. I'm sorry to report I have experience and can prove that golf balls sink when they're struck into lakes and rivers and such. But at any rate, because they're buoyant, the stresses are less. And I could relate to that. I felt I could understand what he was talking about and really started paying attention to him. It turns out in later years, Lymon and I were members of the same golf club and played together quite a few times. And it really was just such a pleasure to get to know him, not only as a teacher, but as a colleague on the golf course and as a friend. So as an undergraduate, I took 3 courses, the Introduction to Geotechnical Engineering class that I've already mentioned. The next class I took was my introduction to Dr. Olson, the Foundation Engineering class. That was more than 50 years ago. And Roy, I'm sorry to report that I don't remember too much of what you taught, but I do have a vivid recollection of one event. One day you came late to class, which was extremely unusual, and you immediately apologized to the class and said, "So sorry, I just got off the phone with someone from," I forget who it was, Golder Associates in Seattle or somebody, and they told you that they'd hire every master's degree graduate that UT produced, send them their way at such and such a salary." And I thought, whoa, a job. And afterwards, I went up to Dr. Olson, and I think I said something like, "What's a master's degree?" I had no idea what it was. But it was funny how just that sort of inclination and off the guard comment to the class was so influential. Well, I really liked that class, and so I took the Earth Slopes and Retaining Structure class. I guess this goes to show what a hopeless engineer I am, because I thought that was truly fascinating. Professor Wright is just a brilliant person and found a way to explain these subjects in fascinating ways. So I just kept going in geotechnical engineering. I have no idea why, but Professor Olson, while I was an undergraduate, hired me to design and build a triaxial cell. I'm sure he probably could have done all this work himself in less time than it took to train me to do it. But nevertheless, he said, "Go build this triaxial cell." It basically was like version 2 or version 3 from one that he had designed and built at the University of Illinois. It was actually a very complex design because it had maybe 30 parts or so. There were O-ring seals and quad ring seals. I didn't know anything about those. I found out, as you can see up here, there was a nut that was knurled. I didn't know you could machine knurled nuts with ball bushings and tolerance to 10,000ths of an inch or so. So I designed the thing, took it down to the machine shop, worked with the machinist, and I'll never forget this moment when I went to pick up all the finished parts. I literally had a box in my hand that had 30 or so parts. And as I walked back to the office, I thought, oh my God, this is never going to work. This stuff is never going to fit. It's never going to work. But you know, it did work. It worked perfectly. I just really couldn't believe it. But this experience had a pretty profound influence on me and in my career. It gave me the confidence, and this is the first of the lessons I'll share with you. Be confident that a good design will work. However, you need to know what you're doing. In my case, I certainly didn't, but Dr. Olson did. Thank you for that. Design it carefully and it will work. So as I went through my whole career, whether I was designing experimental equipment, as you see on the left side, I just knew it would work because of that experience. Even when I became the department head at the University of Illinois, I was confident that if I took the time to understand what the issues were and laid out a careful plan, it too would work. Well, actually, when I got there, their main challenge was they just didn't have enough funded research. And because of that, they weren't recruiting the level of talent of graduate students that they really should have. So we worked that problem. I gave the faculty release time from teaching so they could write major proposals, gave them travel money, gave them administrative support, and we started working more closely with alumni to raise the money that we needed. And it worked. 5 years later, we had grown the research funding from about $4 million a year to about $12 million a year. Folks like Bob Dodds in the structures area partnered with me to recruit much better caliber graduate students, and it just all worked out well. Well, I guess I didn't mess up the Triaxial cell too badly, because Dr. Olson gave me another project as an undergraduate. He had a pile of data on stress strain properties of compacted clay and asked me to analyze the data and fit hyperbolic curves through the stress strain, and including the volumetric stress strain curves. Well, we did that. Of course, he counseled me heavily, and we wound up writing a paper that got published in the Journal of Geotechnical Engineering. I just couldn't believe it. I got published, my first publication. How could that happen? I was just really, really proud of the paper. I must have read that paper 20 times. I was just so amazed that that happened. Well, the opportunity for folks to publish discussions after a paper was published occurred, and Fred Kohlhowie of Cornell University published what I thought was a somewhat critical discussion of the paper. Well, I was just really worked up over that and went in to see Dr. Olson. I think he sort of patted me on the back and said, now, Dave, calm down. So I think I drafted a pretty scathing response to his discussion, and Dr. Olson trimmed that down to about one paragraph or so. That was a very thoughtful and well-worded closure from us. But I was so grateful for that, because I got to know Fred Kohlhowie in the years that followed. He was one of the most fun persons I've ever met to be around, just a real delight, an interesting person. Even after I got my PhD, Fred and Cornell University offered me a faculty position. I wound up going to UT, but I think there's an important lesson there, and that is choose your battles carefully. I've seen so many senior university administrators just really get themselves in trouble by fighting everything. I do think it's important to choose your battles carefully. Well, I went from that to the master's degree program at UT, and Dr. Olson had an NSF project on sand drains. Now, sand drains are vertical columns of sand put in soft compressible clay. As you put fill on clay, it squeezes the water out, much like a wet sponge would be squeezed by your hands. And normally the water would just go up or down to a sand layer. But by installing closely spaced drains, the water can travel a much shorter distance to those drains, get out of the clay a lot faster, and get the settlement and compression over with a lot more quickly. So I wrote a finite difference code to analyze the problem. It's the Terzaghi consolidation equation shown at the top in cylindrical coordinates. This was the basic equation. Actually, the equation's pretty simple. The main problem here was finding someone who could type this back in the day when all we had were manual typewriters. The key thing the program did was track changes in the properties of the soil. And in particular, the coefficient of consolidation is the key parameter. And with the slightly over-consolidated clay at the case history site we were looking at, the Four River site up in Maine, the coefficient of consolidation started pretty high, but because principally of changes in compressibility, wound up a lot lower. So with the code I wrote, we were actually able to track variable soil properties and match the field data. These are the field data, whereas a more traditional analysis with constant soil properties would not do so well. Well, we wrote a paper, and by we, I mean Dr. Olson wrote the paper. I probably drafted the figures, and that was just about it. And lo and behold, it won the Norman Medal of the American Society of Civil Engineers, the highest award in all of civil engineering for all papers published in all of its journals. It was just incredible luck for me that I managed to hitch my wagon to someone who was doing such incredible work. So here's one of the most important lessons I've had from my career, and that is choose your boss carefully. In my case, I stumbled onto working with Roy. This is a picture of him, by the way, on Long's Peak. He once talked me and Fadlo Tuma into trying to climb a mountain with him. It nearly killed me from exhaustion, but he could handle it just fine. As the years went by and opportunities presented themselves, I used this learned lesson to make sure any position I took was one in which the person I was working for really was brilliant, really did have thinking aligned with my thinking, and most importantly, wanted to help me. Bill Showalter, who was the Dean of Engineering at Illinois when I went there, is one of those kinds of people. He's a member of two national academies, just brilliant. Mark Udoff was the Chancellor of the UT system when I was hired to lead UT Dallas. He, too, is a brilliant individual. James Huffines was chairman of the Board of Regents at UT, and it was so critical for me to get things done. I never had any particular desire to go work for the UT system, but when Bill McRaven called me and asked me if I'd help him run the UT system, despite being reluctant about that, as soon as I got to know Bill a bit, he is just one of the most remarkable people anywhere on the planet. And I took the job mostly just to work with him, and I learned a lot doing that. Well, after my master's degree, I went to work with a real job for Woodward Clyde Consultants, later URS, and later others for 3 years in Oakland, California. Boy, was I surprised when I got there. The first thing I discovered was that projects had a scope and budget. Doctors Olson and Wright, you didn't tell me that when I was in grad school, but that's okay. You can't learn everything in school. There are things left to be learned after you leave school. I quickly learned a very important lesson that I kept with me for the rest of my career, and that is the budget really matters. And so a principle I followed is I never attempted anything without a solid and realistic budget and financial plan, unless, of course, it was an emergency and I needed to call 911. For those of you students working on a master's thesis or a PhD dissertation, I can't begin to tell you how valuable that was for me. It taught me how to problem solve, how to write up the results in a reasonably intelligible manner, despite all the red ink that Professor Olson put on my first draft. It did teach me a lot. In essence, it teaches you what the world is like. You're given a problem, you work on it, and you write up the results in a logical and coherent way. It almost doesn't matter what the subject is, it's the process more than the subject that's so valuable. I think the most disappointing aspect was I did find a lot of the work routine. I think I remember saying something like 70% of the work was pretty routine, but some of it was really interesting. I did learn a really valuable lesson at that point, and that is you do have to do the routine work and you do have to do it well. For those who are students, think back to that class you didn't particularly like, taught by that professor you didn't like at all. You know, the students who are successful and earn their degrees are the ones who slug their way through that class and manage to make at least a decent grade, if not better. And when you're a professor, you have to grade papers. That's not a whole lot of fun, but you need to do it well. It's important to the process. And later on, especially as an administrator, all the financial certifications I had to do, I had signature authority and a responsibility and accountability for, you know, massive numbers of things. You just had to slug your way through that, and gosh, meetings, meetings, meetings. So if you're a little bit bored from time to time, just realize you got to hang in there and do it well. You know, in terms of the budget and the financial issue, this was so important to my success to the extent I had any when I was president of UT Dallas. So you may not know much about UT Dallas. That's because they've never lost a football game, because they don't have a football team, and because they don't have a civil engineering program. They were actually started by the founders of Texas Instruments about 50 years ago, and they wanted to create the MIT of the South. In a way, UT Dallas is a little bit maybe like Georgia Tech was 30 years ago, a technology and science-oriented university in a major metro area. At any rate, the university was built right, had a great mission. It just was too small and wasn't scaled up enough. And so we laid out a strategic plan, but I spent more time thinking about how I was actually going to pay for getting all of that done in our wonderful aspirations than I did on what it was we were going to do. So I did develop a financial plan after a lot of thought. One of the first things we did was raise tuition to the point where the tuition was by far the highest of any public university in the state of Texas. I got grief for that, but I just said, this is what we're trying to accomplish. We're trying to build a great university. We can't do it without money. And, you know, if you just want to stamp mediocrity on the title of the university, keep the tuition where it is. So, and again, the chair of the Board of Regents and the Chancellor backed me, and it stuck. I needed a really big boost in state funding and wrote a white paper outlining a plan to do that. And fortunately, Dan Branch, who was a state legislator and lives here in Dallas, not far from me actually, was chair of the Higher Education Committee in the Texas House of Representatives at the time. So we worked closely together, and lo and behold, legislation got passed that pumped about $300 million to UT Dallas over the next few years. I also knew I had to come up with money for new buildings, and thankfully the UT system has a pretty big pot of money, and they were very supportive. Donors were supportive. But at any rate, it's just so, in a way, laughable to me that so many universities have strategic plans that have no possibility for realization because there wasn't a financial plan. But I just trace it back to what I learned as an engineer. I do want to say a word about Lymon Reese, because this is a lecture named in his honor. Lymon taught courses on deep foundations, such as drilled piers, as you see in the diagram here. And he taught us about soil structure interaction. I remember once when I was with Woodward Clyde, someone asked if I'd like to go inspect some drilled piers at Peralta Hospital in Oakland. I said, sure, I'd love to go. So I actually went, and I actually went down the drilled pier to inspect it. This is not me, but this is a photograph. There's the casing, here's the orange vest and the hat. You grab a cable, put your feet on a bucket with a shovel, and go down to the bottom. I was shocked by what I saw when I got to the bottom. I had imagined diagrams like this that were drawn on the blackboard back then with a very clean bottom. I sort of envisioned that one went down with a dustpan and broomed and swept up a couple of specks of dust, and that was about it. It was all wet down there. There was a lot of loose dirt down there. And I saw it and went, oh my gosh, this isn't what it's supposed to look like. But then I thought about Professor Reese and the way he taught us that the skin friction gets mobilized with hardly any deformation. And this end resistance down where it was not quite what I was expected only comes into play after you fully mobilize the skin friction, which basically meant almost none of the load was going to get down to the base of the foundation anyway. And I thought for a moment, you know, if this foundation looks like that, probably a lot of others did too. So I filled the bucket full of soil, and it was actually pretty funny. I was a young engineer, and the concrete truck was ready to pour the concrete. All the construction crew was joking, let's pour it now, while I was still down there. Ha, ha, ha. At any rate, there were many instances where this education about how the earth and the structure interact with one another proved to be very valuable to me. There was another job that taught me a lesson that proved to be extremely valuable through my career at Woodward Clyde. Once we had a little job that had a footing on a slope with an incline and eccentric load in heterogeneous soil conditions. This is about as difficult a footing design as you can come up with, although Dr. Stokey, you're probably saying, yeah, add some dynamic load on top of that, then it's really complicated, and you'd be right about it. At any rate, I took on the assignment. It didn't take a lot of time to analyze it, but it was complicated. And I wrote up a 2-page report to the client telling them what to do, with the last sentence being, therefore, use so-and-so for the bearing pressure on the base of the footing. I handed it to my boss, Ed Margison. He read through it. He kind of nodded affirmatively. Then he took out his red pencil and he struck out everything I wrote except the last sentence, which said, therefore, use the following for the bearing pressure. And he struck therefore and just left, use the following for the bearing pressure. And he looked at me and said, well, Dave, let me tell you, the client doesn't really care about why you did all that sort of thing. All they really care about is what it is they're supposed to do with the result. It was the first time anyone sort of slapped me in the face in a way, and he did it, of course, obviously in a very professional way. but told me to look at the world from the other person's point of view. And I have thought about that lesson learned many, many times. I thought about it as a professor. When I taught, I was considerate of the way that the students might view the way the information was presented. When I spoke with donors, I didn't just talk about what I wanted for the university, but I asked them what they wanted, what their goals were. It was particularly important talking with legislators because they don't have the faintest idea what research is all about or why it's important to the educational process. And if you'll listen to them and talk with them, you'll find ways to communicate with them that are effective. Well, after 3 years at Woodward-Clyde, I considered what was next for me, and I realized my capabilities were lacking in two principal ways. One, I didn't know much of anything about geology, and yet every report we wrote had a discussion of the geology of the site. And because Stokey had not yet arrived at UT Austin, I didn't know anything about soil dynamics. I did notice, however, that one's position at Woodward-Clyde was a function essentially of how much money a person brought into the firm. There were two ways that people essentially brought in money and rose to prominent position in the firm. The first was basically do great work over a period of years, be a terrific engineer, stay on schedule, stay on budget, communicate with the client, be responsive to their needs, and you know what? They'll bring their business back to you. The other was to be a preeminent expert in an emerging field for which there were essentially no other experts. And Eddie Idris at the time was a great example. The San Fernando Valley earthquake had occurred not long before that. Everybody was scrambling to find earthquake experts, and Idris was one of the very few around, and certainly one of the best, and especially with people like Ricardo Dobry that he had on his team. People really just had to go to Idris. He was the best in a rapidly changing field with few experts. So this key lesson I learned, it's the money. That affects, to a large extent, where you're going to wind up in a firm. It may be frustrating. I remember once chatting with a professor who was complaining about how much more money football coaches make than professors. The provost happened to be standing next to me and looked at the professor and said, I'll tell you what, you fill your classroom with 100,000 people paying $100 each, and you get a $20 million a year contract to televise your lectures, and I'll pay you $1 million a year too. You know, it may not be fair, and I would just point out money isn't everything. Well, I was impatient. I wasn't going to take your time and do great work for everyone. That's a fault of mine. And I decided I would get a PhD, shore up my lack of knowledge of geology and soil dynamics. And I wanted to work on a really important problem for which there was little national leadership. And the two that struck me were swelling and expansive soils that damaged so many buildings, and nuclear power plants, which we were building all over the place, but for which we had no idea of what to do with the waste from those power plants. I thought, well, I'll return to engineering practice after that and be better prepared. Well, UT Austin had the perfect research project for me. It was on radioactive waste disposal, sponsored by Los Alamos National Lab, exactly what I wanted to do. By then, Ken Stokey was at UT Austin. I would not have returned to UT had they not had someone who was a preeminent expert in the world in soil dynamics, and I don't know that there's anyone more capable than Ken. So I did my research, which was some finite element analyses, the construction of a kind of unique way of measuring hydraulic conductivity. And I have to say, it was a rather unremarkable dissertation, except for the fact that nobody else was doing anything much like that. I wandered into academia purely by accident, strictly for the reason that it seemed more challenging. I didn't have the faintest idea who would give me any research money, and it scared me to death to think about standing in front of a bunch of brilliant students trying to educate them. But UT offered me a job. It was a wonderful opportunity, and I thank so many people. But as I thought about this, I think the thing that weighed heaviest on my mind was, well, what's the worst that could happen? I could go be a professor, be a complete flop, and return to engineering practice, which was sort of what I had in mind all along. And I have found over the years that asking the question, what's the worst possible thing that can happen? What's the worst outcome? Has been useful to me. I just use one example, was a question of whether we were going to spend $33 million on a new residence hall when I was president. I really didn't think this was a good idea, but all of my leadership team was telling me, go for it, go for it, go for it. And as I thought, well, do I follow their advice or do I follow my instincts? I asked myself, well, what's the worst that could happen? The worst that could happen is the residence hall would sit there empty, and I'd have to pay the debt of a service of $1 to $2 million a year on an empty residence hall. But you know, we could afford that. It wasn't anything all that bad. So we went ahead and did it, and it was just a phenomenal success. We couldn't build residence halls fast enough. They were just so wildly popular with the students. And I'm glad I thought of it that way. You know, what's the worst that could happen? Wasn't that bad. What's the best that could happen? Turned out it was dramatic. Well, that leads into a discussion of risk. And I want to talk about risk. My thinking is heavily influenced by the Deepwater Horizon accident. It killed 11 people and caused $60 billion of damage. I just want to honor the dead who unfortunately lost their lives in this accident. After the accident, the Secretary of the Interior asked Chuck Vest, who was then head of NAE, if the NAE would form a panel to investigate the cause of the failure. Don Winter, who was a former Secretary of Navy, chaired the panel and did a brilliant job. I was fortunate enough to be asked to serve on the panel with just a great group of people. And we did a deep dive on just exactly what went wrong. And I want to talk about that. So the Deepwater Horizon is essentially a ship. It's called a MODU, a mobile offshore drilling unit. It is not anchored when it's drilling. It has dynamic positioning, so propellers in different directions using global position systems keep it in the same location. The well, called the Macondo well, was 48 miles offshore in about 5,000 feet of water. So here's a cross section, not to scale, of the design. This is the Deepwater Horizon ship, a riser pipe down to the wellhead, blowout preventer, and we'll talk at some length about that in a little while, right at the seafloor. A series of telescoping casings with a drill hole down to where the oil is. All of this is about 18,000, 19,000 feet, or on the order of 3 miles down below the ocean floor. Well, the engineers all know that fluid pressure increases more or less linearly with depth. In the ocean, of course, it is essentially linear, but even in the pore fluid within the subsea sediments, think about the water between the golf balls, if you will, increases linearly with depth as well. The petroleum engineering community uses equivalent fluid pressures expressed as pounds per gallon. I'm not aware of anybody else who uses these units, so you'll see this over and over again. And just for point of reference, seawater is about 8.6 pounds per gallon, ordinary water 8.3 pounds per gallon. So when a hole is drilled, casing or a riser is set up to the drill rig. The hole is filled with drilling mud, heavy viscous mud. The fluid level is maintained higher in the hole than the surrounding water level so that the mud tends to flow out into the formation. It forms a thin filter cake as it flows out. Think about your coffee grounds and your coffee filter if you're not an engineer. Forms kind of a membrane, and the pressure then from the mud pushing outward keeps the hole open. So the water pressure increases more or less linearly with depth. So does the mud pressure, but the mud is heavier than water, so it keeps increasing in space between it. Unfortunately, you can put enough pressure in the ground to actually fracture the ground. The pressure can exceed the stresses in the ground, open a horizontal crack and lift the ground, open a vertical crack and separate the ground horizontally. This is exactly how fracking works in oil extraction. You put high pressure in the ground, fracture it, and then extract the fluid. In oil exploration, for purposes like this, fracturing is not a good thing. So what happens if you happen to hit a zone, and of course the geology is variable when you fracture the formation. Let's say you drill down into a zone where the fracture pressure is less than the fluid pressure. The fluid just pushes out into the fracture zone, and you immediately have to start pumping a whole lot more mud in, otherwise the fluid level will drop and the hole could collapse. In some ways, an even worse situation is what the industry calls a kick, when the pressure in an overpressurized formation actually forces the fluid from that formation into the well. If this fluid in this overpressurized formation is oil and gas, for example, and there's enough pressure and enough flow, you can actually get a blowout where the pressures overcome the drilling mud. And of course, that's a disastrous consequence. It's common in the industry, in fact, good practice, to monitor the rate of mud flow into a well and the rate coming out of a well. So the way this works is there's a drill pipe with a cutting bit down at the end of the drill pipe. The viscous mud is pumped down the drill pipe as drilling occurs. The liquid then carries the rock that's cut away by the drill bit up in the mud in the annular space between the drill pipe and the casing and the riser, out into a mud pit where the stuff that's drilled away is monitored to see if it's what it's supposed to be, then is cleaned up and pumped back down the hole. When things are going well, the fluid coming in and the fluid going out are about the same. If you have a kick, for example, what it means is the amount of mud coming out is much greater than the amount of mud coming in. And of course, that could be a precursor for a blowout and is a very, very dangerous situation. This is from the BP plans for the drilling operation. It's a complex diagram, and I just want to make a couple of points about it. It's obviously not to scale. This is like 3 miles long and 2 feet wide. But the casings are set at in a telescoping manner as they drill down deeper and deeper. So they'll drill a while, they'll stop, set another casing, drill a while or a liner, set another casing, and so forth. And then when all is done, they'll put a pipe in the middle, as we'll see, that's called the production casing. So that's the plan. This is a rather complicated diagram, but it's an important one. And if you'll give me a moment, let me walk you through this diagram. So this is a graph of depth below the water surface on the vertical axis, and on the abscissa, equivalent fluid pressure, again, using these units the petroleum people like, pounds per gallon. So the leftmost line or set of lines is the formation pressure or pore water pressure estimated before the job in the formation. So it increases, not exactly linearly with depth, but more or less linearly with depth. Let me come over here to the right-hand side and show you the fracture pressure. This is the estimated pressure that would cause hydraulic fracturing. So in the drilling operation, the actual mud weight, and that's this red curve in the middle, absolutely has to be between these two extremes, and it is. But it's also required by the federal government that there be a factor of safety applied to the fracture pressure and the formation pressure. And that requirement is that the mud pressure must be equal to the formation pressure plus 0.2 pounds per gallon equivalent fluid pressure, and it must be less than the fracture pressure minus 0.5 pounds per gallon. So think of this as a car driving down the highway, and these are the lane markers. The mud weight has to be between the lane markers. You may wonder why there are these discontinuous jumps like this one, for example. And that's because as one is drilling down, you need to increase the mud weight at this depth, otherwise you're at risk of a kick. So they stop at that point and set another casing of smaller diameter, another telescoping casing down to that depth. That enables them then to increase the pressure because everything above has been cased off, drill down, then set another casing, and so on and so forth. Well, they were drilling away. Lots of problems happened, as is to be expected. A particularly significant event occurred April 4th to 7th, when they were a little over 18,000 feet down. They lost circulation. About 3,000 more barrels of drilling mud went down into the hole than came back out of the hole. And that's about one whole well bore volume, counting the riser up to the surface. That's a lot of mud to lose a whole well bore volume. Well, the way the industry deals with this is to pump in a thick, viscous mud with a bunch of stuff added to it that they call a kill pill to sort of seal up these fractures that have inadvertently occurred. So they were able to do that and continue drilling. But it's clear that the BP and Transocean and other folks viewed this risk of fracking and loss of well fluid as the #1 risk and put it, really in their vision as the thing to avoid. By April 9th, they had reached a depth of 18,360 feet, and they decided at that point to stop and drill no further. They said that they had essentially run out of drilling margin. The difference between the fracture pressure and the pore water pressure was only about 0.2 pounds per gallon. It's as if the lane in which you're driving your car is narrowed that you could almost stick your finger out the window and touch the truck next to you. There just was no more space left, so they stopped. They had originally planned to drill down deeper to over 19,000 feet. Shouldn't feel too sorry for them for not getting that last 1,000 feet. They still estimated they had 50 million barrels of oil in the pay zone, even at that depth. Well, at that point, the next step in the process is to clean out the hole because it's probably got sediment in it. The industry calls this pumping bottoms up. So the plan here is that you pump fresh mud in, it circulates up the annulus and out so that you get rid of all this kind of gunky mud with sediment, especially the sediment that is accumulated down at the bottom. And you sort of clean off the sides of the pipe so when this gets cemented up, you'll have good bonding. About 2,700 barrels of flow were needed to do a full bottoms up, that is to say, flush all the remnant mud out and replace it with fresh mud. They pumped about 350 barrels and then decided to stop. And they stopped because they felt that the pressures they were putting on the production casing to force the mud down were just too high. They were too worried about fracture, too worried about loss of drilling fluid that they decided to stop, which raises the question, what was down here in the bottom of the hole? Was there a bunch of sediment or was it relatively clean? Well, once the bottoms up is done, which it really wasn't done, the next step is to set the production casing. It was actually a telescoping casing with 2 diameters, 9 7/8 in the upper reach, 7 inches in the bottom reach, and about 13,000 feet long. The blowout preventer sits at the mud line, riser pipe, and drilling mud. There are 2 cement seals. Here's the plan for the cement seals for the production casing. One of the cement seals is the annular space between the production casing and the telescoping casing that holds the hole open. The other plug is the cement plug at the bottom of the production casing. After the cement is set, the blowout preventer is removed, the riser is removed, and Deepwater Horizon leaves the site. This is called temporary abandonment. Later, the owner comes back with a much smaller boat, a much less expensive boat, penetrates through this, sets up appropriate controls, blasts and opens up the cavities down here, and begins producing oil. But the key now is to seal up the bottom of the hole so they can walk away from it and nothing bad happens. Well, this production casing, which is 7 to 9 7/8 inches in outside diameter, is about 13,000 feet long. It has a length to diameter ratio of 16 to 22,000, and it has a weight on the order of 60,000 pounds. Of course, anytime you have a long, slender column, it tends to have buckling. So again, for the non-engineer, I have my plastic ruler. If you push on the ends, it tends to buckle. And that's what would tend to happen with the production casing in the ground. So to stop that from being a problem, it's important to make sure that the production casing is in the middle of the well. If the production casing is in the middle of the well, the annular space that's cemented in will have a nice uniform distribution of cement grout around it. If the casing has buckled and is over against the wall of the hole, the mud will be trapped in here and the cement will not penetrate. After you walk away, then this mud can be washed away and leakage can occur in the annular space. This, by the way, is called a SUB centralizer, and this is attached between two sections of casing, and these little things here keep the casing centered in the hole. Well, industry computer codes are available to tell you how many centralizers you need for pipe, and those codes indicated that they needed 21 centralizers over this 13,000-foot depth. 6 centralizers were available on the Deepwater horizon, so they ordered some more at the last minute, 15 more, which were delivered, but they weren't identical to the types of spacers that had been ordered. So at a last moment, they decided, well, we'll just leave the spacers out and we'll just go with the 6 originally designed rather than the 21 that the analysis indicated was necessary. Well, now it's time to seal up the bottom of the hole. The industry uses something called a float valve assembly, and I'm going to explain that in just a moment. But here from the bottom up is what this assembly looks like. At the very bottom of the production casing is a reamer. That's just there to center the hole. There are openings here so that as the casing is lowered down, the fluid, the mud, can come up into the hole. I'll explain this float valve assembly in just a moment. In fact, let me do that right now. Again, this is a little bit of a complicated diagram, but if you'll bear with me, let me take a moment to explain how this works. So the casing in step 1 is being lowered down, the production casing, to the bottom of the well. To make life simple, as you lower this down, you need the pipe to fill with mud. And rather than pour it in from the top, which can be slow, time-consuming, and expensive, it's faster just to have the bottom open and let the mud flow upward. So there's something called an autofilled tube here between a couple of flappers. I'll explain that too in a minute. But as the casing is lowered, the mud, actually this ball is lifted and the mud flows around the ball. There are some holes too, and the mud flows up. So essentially, this is like a one-way tube that lets liquid flow upward as the casing is lowered. So now imagine that the casing is at the bottom of the hole and it's time to do something the industry calls converting the flow collar. And what they do is they put a pressure on top of this autofill tube. The little ball valve, which was up here when there was flow, is forced down to the bottom. Fluid can still get through these tiny ports, but if you put enough pressure, essentially you blow this tube out of its position in the collar and it falls to the bottom, as you've seen here. These flapper valves are much like, at least conceptually, the valves in the bowl behind your toilet. If you've ever lifted the top off your toilet and looked at that flapper, it's sort of like that, upside down, but with springs on it. At any rate, this is called converting the flow collar when you force that tube down. Then you pump cement down to grout this up. As the cement flows down, the flappers will open up. They're like one-way valves to let the cement in. And when all is done, you've got cement and you've got flappers, a redundant system to stop anything from flowing back up if everything goes well. Okay, so it was time to convert the flow valves. The manufacturer's specification says that you need to put at least 600 psi of differential pressure and achieve at least 6 barrels per minute of flow in order to force that tube out. Well, BP sequentially increased the pressure starting at about 600 psi, but they couldn't get any flow. Finally, on their 9th attempt, they jacked the pressure up to 3142 psi. That's a phenomenal pressure, actually. And this pressure suddenly dropped and the flow rate increased, which was a good sign if you want to blow that tube out of there. But they never got the flow rate above 4 barrels per minute. So BP concluded that the float valves had converted. Why? We don't know. The NAE panel concluded that they had probably not converted. Why? Because they never got close to 6 barrels per minute of flow. The fact that the first 8 attempts did not evidently move the tube indicates to us that the sediment, which probably was there, at least to some extent, was blocking the downward movement of the autofill tube. And also, after they turned off the pump, pumping the cement down into the bottom, when you turn the pressure off, you get a little bit of flow back up to the surface just because the reduction of the pressure causes expansion of the liquid. They got about 5.5 barrels of flow back up to the surface after they shut off the pump, but they should have only gotten about 3 barrels of flow just from the compressibility of the liquid. We think that that probably was leakage through the valves. Okay, so it's now time to cement. They could not pump regular cement down to the bottom of the hole because it was too heavy. They would have fractured the formation. So they used foam cement, that is to say, cement entrained with nitrogen. This is really remarkable stuff and a challenge. The temperature at the bottom of the well was 275 degrees and the pressure was a remarkable 1321. So the idea was, how do you make a cement that's got so much air into it that by the time it gets to 13,000 psi pressure, it has the desired density? And the answer is you entrain a bunch of nitrogen air into it such that it has a density even at 600 psi. That's a really high pressure of 6 pounds per gallon. That's a lot lighter than water. So I want you to think of this cement more like shaving cream than you would think of as the cement that's poured out of a cement truck. Well, at any rate, in terms of designing this foam mix, which you can imagine was pretty much of a challenge, a preliminary test was done by Halliburton in February, but the mixture was unstable. They waited until the well was almost complete because they wanted to get accurate information on temperature and pressure. So on April 13th, they tried making up another mix, but it was not stable. It meant that the nitrogen air came out of the mixture and uniform results did not occur. The results were evidently not reported to BP. Doesn't matter because Halliburton basically redid the test. They doubled the conditioning time, but the BP folks decided to go ahead and pour the cement job at the well before those test results were available. In the interest of time, I think I'm going to skip over this quickly, and I'm just going to say that there are predictive models for what foam cement strengths might look like. And those predictive models showed that at best, the foam cement was marginal, at best, with no factor of safety. BP performed tests on similar cement after the disaster, and they concluded that the foam cement slurry for the Macondo well was likely unstable, resulting in nitrogen breakout. It's absolutely shocking to me that they proceeded for such a critical structure with no test. Well, not to worry, they had yet another test that should have given them a clear answer. It's called a negative pressure test. So they've put these cement seals in place. The plan is that they pump the mud out of the production casing, and that lowers the pressure inside of the production casing. So now the pressure is higher and the flow rate, replacing heavy mud with light water, is up. So if the seals work, there won't be any flow. If the seals fail to work, there will be flow. So they actually sealed things off and measure the flow and the pressure up the top. So on April 20th, the first attempt where they should get no flow and no pressure, they got 1,200 psi of pressure. They tried it again. They got 770 psi. They did it again and again and again and got more than 1,000 psi. The BP person, so-called company man, explained away the effect as the bladder effect. None of us had ever heard of bladder effect used in the industry, and certainly not for this application. They tried a different valve scheme using a valve on the blowout preventer rather than one up at the drill pipe, and this one produced no flow as they had hoped for, but produced a pressure in the drill pipe of 1,400 psi. At the best, I think you would say these are very ambiguous results. BP decided that the test was a success and proceeded. In my mind, this was the most devastatingly bad decision when at best the test results were ambiguous and at worst they indicated that the seals wouldn't work. So on April 20th at 8 p.m., they began with the temporary abandonment, and that meant pumping all the mud out of the riser and out of the well, but they were not monitoring the inflow and outflow. Afterwards, I think it was pretty clear that there was a lot more outflow than inflow because the blowout was initiating. They did monitor the pressure in the blowout preventer as they were just removing the mud and replacing it with water. As they took the heavy mud out and put water in, the pressure actually should have gone down inside the blowout preventer, but it was actually going up. They weren't watching that and missed a warning sign. And as you can see, a blowout occurred at 9:48 p.m. The power generators on top of the deck of Deepwater Horizon started sucking in natural gas rather than air to drive the engine. That caused the generators to greatly overspeed because the input was natural gas, not air. And they shut down and failed because of that, causing the ship to lose power. Well, you know, I put this slide up and the comments up because as we engineers do our calculations, I think sometimes we forget that there are people involved. And back to my comment earlier, when I think about risk, what's the worst that can happen? In this case, it was just really, really awful. Just a few words about the blowout preventer. This is a massive structure. This is actually the blowout preventer months later, removed from the bottom of the ocean and returned to a location in New Orleans. The key is this blind shear ram that I'll explain in a moment. This is a giant device that'll just slice off the pipe. When you push a button, it just shears off the pipe and shuts the well down completely. Obviously, you don't push this button very often because it's quite a mess to come back in and undo that. But for this to work, the pipe is supposed to be centered. It's supposed to be under tension. Imagine if you're cutting a string with a pair of scissors. It's a lot easier to cut the string when it's taut than when it's not taut. And it turns out that you can't have the pipe tool joints in the path of the shear ram. It won't cut the joints. It's not designed to cut these joints. So these are the so-called tool joints in drill pipes. And Professor Gilbert, this one's for you. So I don't know what percentage of this pipe is tool joints, but I'm guessing maybe 5% of the pipe is tool joints, which means that by design, unless you can take the time to carefully control the position of the tool joint, you've got a 5% chance when you shear of hitting the tool joint and it not working. And to me, that's just an unacceptably high probability of failure. Imagine if you had airbags in automobiles, also your last line of defense, and 5% of all the airbags would fail. Can you imagine how utterly unacceptable that would be? Well, at any rate, the derrick had blown out by then. The pipe was under compression. It had drifted off to the side. The tool of this shear ram is actually not designed to cut when it's off to the side like this. These are results of finite element analysis that shows what would happen if the pipe is off to the side. This is actually a photograph of the drill pipe recovered months after the failure. And this is actually where all the leakage occurred, right through that unsheared section. So what are the lessons that we learned from this that might be applicable to other endeavors? To me, their number one problem was complacency. You know, nothing bad had happened for a long, long time. Complacency is so hard to avoid. I mean, just think about it. We drive our car, we speed, nothing ever happened before. We're on the cell phone on our car, nothing ever bad happened before. I think this avoidance of complacency is one of the hardest things to overcome. A lot of people question whether BP put budget above safety. I'm not going to try to answer that question, but I can tell you as a president, nobody ever was allowed to use a budget as an excuse for not addressing safety issues. I had a couple of people, when I asked them why we hadn't fixed a trip and fall hazard, they said, well, there's not enough budget for it. And I said, I don't ever want to hear that again, ever. When you've got a safety problem, you've got a budget, come talk to me if you need it. And also the folks on the boat were exhausted, they were over budget, they were over schedule, they were all ready to go home. And they weren't really getting any independent advice from people who were not caught up in the heat of the moment. If there's time, you need to do that. Well, I'll finish up after my geotechnical career. I have learned some additional lessons, and to the faculty, this did not come from any of you, none of you are weird, but I have discovered some people are just weird. And sometimes in trying to make a situation better, I think I just made it worse. My advice to you is if you encounter such a person, and I'm not talking about illegal or unethical or inappropriate behavior, just immature and annoying behavior, my advice is just stay away from it. The other thing I've noticed is in making key decisions, you just have to realize your job is, at least as a university administrator, is to serve the students and faculty and the taxpayers and families that pay for it all. And if you need to fire someone because they're not good enough as a teacher or as an administrator, do it and don't lose sleep over it. Your responsibility is to the people you're serving. And you know, there are some people, wonderful people, who just can't do that. They take everything personally. And there's nothing wrong with that. Just don't get into a job of administration where that's part of the job responsibility. And the last one is I'd note that it's okay not to have a career plan. I never did. All of those jobs I took were purely by accident, mostly because somebody I admired came and asked me if I'd be willing to do it. So Professor Olson, never once did you say, Dave, what are you going to be doing in 5 years? And I'm glad you never did, because I would have said, I have no idea what I'm going to be doing in 5 years. As I reflect on what the geotechnical program taught me anyway, I think about something one UT Dallas alum told me once when I met with him in Hong Kong and asked him, what was it about your university experience that was so valuable to you? And he answered, he thought for a moment, he said, you taught me a way of thinking. And I think that phrase exactly and precisely captures why I'm so grateful to my geotechnical engineering education. You taught me a way of thinking that proved invaluable in so many ways. So to each of you, I say thank you. And Bill Eisenhower, who gave me the picture of me and Lymon on the occasion of his 90th birthday, thank you all. You made such a big difference in my life in ways maybe you don't even realize. And to my former students, you were the ones who did all the work. You were the brilliant ones. I was just there trying to bring in the money so you could do the work. And not only were they just wonderful, wonderful people, but they were also people who loved to have fun and enjoy life. I thank each of you for staying with me in this lecture. Steve Troutwine, shown in this picture with Lymon, also provided a photograph. Thank you for that. And I would just say, as I draw toward the end of my professional career, if I think of one final lesson, it's that personal relationships and friendships are what you remember the most and what you treasure the most. So thank you once again. And Dr. Rathje, back to you.
Thank you, Dave. That was an amazing talk. I love the way you were able to weave together the technical and the non-technical. Absolutely. We did not coordinate on the idea of Lymon not necessarily having a career plan in the beginning of his life as well as yours. So that really hit home. And I love that you ended with the golf picture, because any other year we would have been having a golf tournament tomorrow, although the weather is supposed to be cold tomorrow. So maybe it's good that we're not, but next year we definitely will. So I know that Dr. Olson would love to say a few words. I also want some of those pictures of Dr. Olson that you showed, Dave.
Can do.
So go ahead, Roy and Bob.
Yeah, well, here's Dave's master thesis on Roy's desk when I walked in here this afternoon. And Roy thought it was a fantastic lecture. He didn't prepare to say anything, so he just wants to say hi to everyone. And in the reception, he'll get a chance to talk to people individually. So he looks forward to that.
Thanks, Bob, and thank you, Roy.
Yeah, it's so good to see you. We do have one question here from Norm Dennis.
Hi, Norm.
He says, about 15 years ago, you told me your best research ideas were still on the shelf. Do you have any plans to dust them off? Can you share?
You know, I don't know that they're the best ideas, but I sure wish I were a PhD student. And I'll apply that same principle I talked about earlier. What are the biggest problems out there where there's really not much leadership right now? That's where I would go once again. And right now, the thing that interests me the most is what to do about all the carbon in the atmosphere. I mean, it came from the ground, and in my mind, it needs to go back to the ground. How do we sequester carbon? How do we get it back in the ground? How do we keep it there for millennia? there's a huge problem. And I don't think there are many people out there doing that. So I don't think that's my best idea. I don't think I ever had very many good ideas, but I do have a sense of where the problems are. And I do know from experience that great leaders like the geotechnical engineering faculty are going to be the ones who solve it.
Great. Well, I do not see any other questions in there. So this is just like in class, right? We should count to 10 and see if anyone else decides to have a question. I love the fact that you really went through the details of the Deepwater Horizon. I haven't seen such a thorough explanation. I really appreciated that. Okay, so that worked. We have another question. You mentioned budget matters. This comes from Jinbo Chen. You mentioned budget matters and money is important. So what is your strategy to balance the engineering ethics and project economics resulting from your design, especially when it involves big money?
You know, that's such a hard one. And I don't have an answer for it, but I do have sort of a personal answer. I remember once I was working on a landfill project, and I was hired as a consultant to help them with the problem. And I was sitting in the trailer on the job site, and the engineering company that was doing quality control testing, Bob will remember this kind of testing from years ago, was talking to the owner of the project and complaining that they, basically had worked them down to a lower price. They had agreed to do fewer tests, and the owner was saying, I want you to write the certification letter to the regulatory agency saying everything's okay. And the consultant said, no, that's not what we agreed on. We agreed that if I was going to do fewer tests, you were going to sign the certification letter, not me. And I wasn't involved in this. I was just sitting there watching it. But it just reminded me that sometimes the best thing to do is to walk away. And I think this is the hardest thing for engineers to do, is to walk away from an unsuitable situation. You know, with Deepwater Horizon, ExxonMobil had encountered a somewhat similar situation with a deep water well in the Gulf of Mexico a few years earlier, and they just decided to abandon the well. They walked away from a $100 million investment. And can you imagine sort of the tension? Of course, the CEO at the time, Rex Tillerson, is a civil engineering alum. And actually, just as another aside, I went and looked at who was on the board of directors of BP at the time this happened, and there were essentially no engineers or scientists. They were all financial people and marketing people. And so my only advice about budget is back to that comment about safety. You will never let budget compromise safety. And if you're ever asked to be put into that position, I'd walk away from it, and I'd go consult my my ethics people on what my obligations and responsibilities are to report.
Great, thank you. We have a couple more questions here. So Rodolfo Sancio is, of course, saying it was an excellent presentation, and he'd like to share it with his team. Will it be okay if we share this recording?
Happy for you to do that.
Okay, wonderful.
Just give people a no-dose pill before they watch it.
No. And then Susan Burns from Georgia Tech is asked, in what ways do you think your preparation in geotechnical engineering uniquely prepared you to lead as an administrator, thinking about uncertainty and those type of related issues?
You know, I never planned to be an administrator. It all happened by accident. I mean, Mike Walton asked me to be an associate chair. Bob Gilbert sitting there. I would have never gone to Illinois if he hadn't parked himself in my office and not left until I agreed to at least go up there and check it out. So I don't really know. I did have a successful run, as it turned out, in those positions. And I really do think the principles I taught, just hanging around Roy Olson and Steve Wright and Lyman Reese and Ken Stokey, these are people of principle. They're organized people. They're serious people, but they're also great human beings as well. And I remember the geotech student parties. We could have fun. We knew how to have fun. And I don't know why Roy Olson thought climbing Long's Peak was fun, but there are different variants of fun in doing that. So Susan, you'll have to figure that one out for yourself.
Okay, so we have one more question, but I know a couple of people have raised their hands, and what we need you to do, if you're raising your hand to ask a question, please type the question. So we may have a couple more after they come in here. So, but Jim Munson says, the The Deep Horizon failure bears a striking relationship to the Chernobyl nuclear plant failure, insofar as there were numerous occasions for decision makers to have the courage to make the more prudent choice. So what were some of the human-related factors that contributed to the failure?
I think the human-related factors were budget and schedule. The project was over budget. I think people were under tremendous pressure. You know, the industry would say of the 120 or so people on the drill rig at any one time, any one of those 120, if they see a safety issue, can effectively order the stopping of operations. And they say, see how safe things are? Any one of the 120 can stop it at any time if they see anything. Now think about the real world, right? That's about like pushing that button with the blind shear ram. You know, anybody could push that button, but when you push that button, you know, chaos ensues. And so I think the safety culture is really, really a challenge. And I don't have any easy answers for this, but how you avoid complacency, how you make safety actually work, not just on paper, but in reality, I think it's actually all human. You know, you look at what happened, and there was nothing mysteriously, you know, nothing scientific or engineering that was mysterious about it. It was just a series of really bad decisions where it's hard to imagine how or why, with hindsight, they occurred. And I can only conclude in the heat of the moment, for whatever drives human behavior in the heat of the moment. You know, I'll tell one quick story. I was talking to, when I was president, our university police chief, and he was telling me he needed more money because they were having trouble staffing essentially the police radio in headquarters in the middle of the night. And I said, well, why do you have to do that? And he said, well, an officer who's going to stop anybody or do anything has to phone into headquarters. And I said, why is that? And he said, well, actually, the reason is we want to calm the situation down. We want to calm that officer down by them being required to pick up the radio and phone back to headquarters and talk to someone at headquarters. It's been shown that that can stop some stupid things from happening just from a little bit of human communication. And particularly, I think if there were people on shore who were required to review it, who sort of didn't have a dog in the fight out there, it would have been much, much better.
Okay, so now we have a very technical question from Bill Eisenhower. Do you still use a daytimer diary?
Well, Professor Olson taught me that. I finally abandoned that, but Olson kept track, Roy, I hope you remember this, every minute of every day you'd write down what you did, which I never got quite that serious, but I did carry that around.
I'm gonna, this is gonna be the last question by Magid Iskander.
Hi, Magid.
Thanks for the excellent presentation. You were, as I did not happen to mention, but it's in the write-up, you were involved both, Dave, in the investigations for after Hurricane Katrina and the Deepwater Horizon. So apart from money being the root cause of those failures, were there anything else in common that you can see?
Well, I think the overriding commonality was safety was not a priority in either case. It just wasn't the driving priority in Deepwater Horizon, and it certainly wasn't with the New Orleans levees. The levees were a lot more complicated because the federal government and the US Congress were involved. But ultimately, and I didn't include this in the talk, but I have a similar talk on the 17th Street Canal failure, and I'm sure the faculty talk about that in your lectures. But it also was just a series of mysteriously stupid decisions, actually, where they took an unconservative interpretation of shear strength. Why on earth anyone would do that? Somebody actually ran a test, the E99 test, that showed even though they had calculated a factor of safety of 1.47, it was really 1.0, and nobody did anything about it. I think it's all about people, and it's about human behavior. So for you engineers, maybe it's good to learn a little bit about human behavior and safety culture.
Great. And I want to end with a comment that came in the chat, actually, from Jerry Eichholt, who said,
hey, Jerry, he was one of those smiling people.
He said, working in your lab was a real lesson in itself. You had great tools and a playground of equipment. I know many students helped build it, but I wanted to say you set a great culture for learning. And so I think that's a great way to end. But this